Hi folks, welcome to your second video in the 9.2 notes, and we're going to talk about an application of when we might use separation of variables. So let's get started. Example number 4, mothballs of a certain brand evaporate at a rate proportional to their volume, losing half of their volume every 4 weeks. If the volume of the mothball is initially 15 cubic centimeters and a mothball becomes ineffective when its volume reaches 1 cubic centimeter, how long will these mothballs be effective? Okay, so a couple things that we see here that would be important to note, all right? We have that these mothballs are evaporating at a rate proportional to their volume. And the moment I see that there's like a rate proportional to something, I'm thinking, okay, the change in the volume with respect to time, so dV dt, is going to equal K times V. So this K is that rate proportionality constant, all right? And so in order to solve this question, we need to find out what K is, and we're going to do that by integrating so we can find this particular function. But then they also give us some other pieces of information that maybe we should write down now because these will count as sort of like our way of helping us find the K value at the end of the day. Right. So it tells us that the volume of each mothball is initially 15 cubic centimeters. And what that means is that our volume at time zero is 15 cubic centimeters. Okay. Oops. It also tells us, oh goodness. It also tells us some other number. So let's see what this number is. It says that the mothball becomes ineffective when its volume reaches 1 cubic centimeter. So we're going to use that at the end to help us figure out some more information. So let's kind of hold off on that piece. But there is one last piece of information here, which is that we are losing half the volume every 4 weeks. And so what that means is in 4 weeks' time, we're going to have half of 15 or 7.5 cubic centimeters left. Okay. And so this is not so clearly stated as a number, but I think when we read the question carefully, can see like where it's telling us that. Okay. And so what we're going to do first is we're going to go ahead and separate our variables so that we can integrate and see what our general solution is, okay? Once we find our general solution, we're going to use this other information to help us find exactly what our t value is so we know how long, okay? All right, so first step, we're going to go ahead and find our solution. Okay, our general solution. And so I'm going to take this dV dt equals kV, and I'm going to separate all my v dv's on one side and all my constants and t's on the other side. So I'm going to have 1 over v dv equals k dt. Okay, so I've gone ahead and separated. Now I'm going to integrate both sides. And when I do that, I get the natural log of the absolute value of v on the left-hand side. And on the right-hand side, I get kt plus c. Okay. Now to get rid of this natural log so we can get our v all by itself, we are going to put e to the power of both sides. So e to the natural log of the absolute value of v equals e to the kt plus c, right? And this step has a fancy word. It's called exponentiate, okay? And so what we're doing here is we're saying, let's e both sides so that we can get rid of that natural log part and go ahead and find our v. okay? So once we exponentiate, we get V equals e to the kt times e to the c. And this is a property of exponents, okay? So when we're adding our exponents, we can go ahead and break them down to the first one times the second one. Now, don't forget that e to the c is just a number, so let's write this as v equals a e to the kt, all right? And what we have here is our general solution. But what we still need to find, we need to find a number for A and we need to find a number for K. Once we find our number for A and K, that will help us find our T number that we're interested in at the end of the day. Okay? So let's go ahead and do our step 2 where we find our A and our K values. Okay? And so at this point, it's going to require a lot of substitution. We're going to be using this green and blue highlighted information to help us find our A value and our K value. Okay. So I've got V equals AE to the KT. Let me go ahead and plug in 0 for T and 15 in for my V. And I think that's going to help us find our A value. Okay, so 15 equals AE to the 0. We know that E to the 0 is 1. So this shows us that A is equal to 15. Okay, and so let's add that information into there. V equals 15e to the kt. All right, so we've got our A value. Now let's use this second point to help us figure out what our K value is, okay? So I get 7.5 equals 15e to the 4k. I'm going to go ahead and divide both sides by 15. That gives me 0.5 equals e to the 4k. I'm going to natural log both sides. Natural log of 0.5 equals 4k. And then I'm going to divide by 4. So I get natural log of 0.5 divided by 4 is my k value. If I put this into the calculator, I end up with negative 0.1733, and it kind of keeps going from there. So we'll just have like a ... okay? But now that I found my A and my K, I can go ahead and write my entire equation. So volume equals 15 E to the negative 0.1733 T, okay? So this was the end goal of step 2. But the third and final step, we want to go ahead and find out how long until this mothball is only 1 cubic centimeter big, okay? So we're going to, as our third step, solve for T, okay? All right, so I've got 1 equals 15e to the negative 0.1733 t. 1 because that's how big I want the mothball to be. I know after that it's no longer working. And then it equals my volume equation with all the letters that I just found. This is going to work very similarly to this step over here. Instead of dividing 7.5 by 15, I'm going to divide 1 by 15, okay? And after that, I'm going to natural log both sides. And after that, I'm going to divide by that coefficient of k, all right? So that's going to look like 1 over 15 equals e to the negative 0.1733t. Now I'm going to natural log both sides. So natural log of 1 over 1/15 equals negative 0.1733t. Now I'm going to go ahead and divide both sides by negative 0.1733, and I'll get t equals natural log of 1 over 15 divided by negative 0.1733. And when I type that all out in the calculator, I get about 15.6 weeks. Okay. So in other words, these mothballs are good for almost 16 weeks, almost like a full semester, 15 weeks, and then they're pretty much done and we got to replace them. Okay. So let me know if you have any questions. I hope this was helpful.